Welcome to this explainer, where we're going to dive into the invisible, high-stakes battle happening right now on our power grid just to keep your lights on safely. We completely take for granted that when we flip a switch, the lights just pop on. But behind that incredibly simple action is this massive, beautifully complex system that is literally constantly under threat. So today, we're going to break down the anatomy of a grid crisis. We'll look at how faults occur, how our power system spots them in the blink of an eye, and the extreme engineering required to prevent a total, widespread blackout.
Okay, let's jump right into this. To really understand the grid, we have to start by establishing the stakes. What actually happens in the milliseconds after, say, lightning strikes a power line? Well, a grid fault isn't just a minor glitch. It's not a tiny little spark. It is a massive, violent burst of rogue energy that essentially breaks the rules of physics as the system intended them. It's the kind of event that demands an absolute, immediate, and forceful response. Because if it doesn't get one, the entire network could just come crashing down.
So first things first, let's define what we're actually talking about here. A fault is basically any abnormal condition in a power system that disrupts the normal flow of current. It usually creates an unintentional path for current to flow, which we call a short circuit, or it interrupts the current entirely, which is an open circuit. Think of a fault as the crime in our story. It's this dangerous anomaly introducing a completely unintentional path for extreme current, and it demands immediate justice to protect the rest of the electrical community.
Now, we kind of group these electrical crimes into two main buckets based on how they affect the three phases of our power system. Phases A, B, and C. On one side, we have symmetrical or balanced faults. This is the big one. All three phases are affected equally, meaning the fault currents are equal in magnitude and separated by a perfect 120-degree angle. This happens when all three lines short together. On the flip side, we have unsymmetrical or unbalanced faults. These introduce total chaos, unequal currents, irregular phase displacements. So we're essentially comparing the catastrophic but super rare symmetrical faults against the everyday chaotic, unbalanced ones.
What's genuinely wild here is the breakdown of how often these things actually happen. You think total three-phase meltdowns happen all the time, right? Actually, no. Symmetrical faults make up less than 5% of all transmission line faults. They are absolutely the most severe, but thankfully super rare. On the other hand, almost all of our grid chaos comes down to a single line just touching the ground or a neutral wire. That's a single line to ground fault, and it accounts for a staggering 70% of all faults. The remaining 25% are your other unsymmetrical faults, like maybe two lines swinging into each other during a bad storm.
Section 1. The everyday villains. What causes grid chaos?
Let's look at the actual culprits that trigger these massive electrical crises in the real world. You might be surprised by what can actually bring down a high-voltage tower. Sure, we have the obvious environmental stuff. Massive lightning strikes, heavy winds throwing lines together, ice literally dragging lines down to the earth. Then there's equipment failure, just the everyday degradation of insulation over time. We've also got human error. Think accidental digging into underground cables or just simple switching mistakes. But honestly, what I find fascinating is that last bullet point, animals. Alongside massive lightning strikes, it is literally wild to consider that a single squirrel, a bird, or a mouse can completely threaten a massive industrial power grid just by crossing the wrong two wires.
Section 2. The brain. Protective relays. All right, so with the threat established and our villains identified, let's meet the high-tech detective of our story, the protective relay. But here's the catch. Because our brilliant relay brain is so incredibly sophisticated, it's actually way too fragile to handle the massive high voltages of the main grid directly. It would fry instantly. So it relies entirely on these components called instrument transformers to act as its eyes and ears. These step down those extreme system values to safe, low-level signals that the relay can continuously and safely monitor.
So how does it spot a crime? The relay continuously analyzes those step-down signals using a few distinct methods. It does overcurrent detection, basically tripping if the current spikes drastically above a set limit. It watches for under or over voltage, because a sudden voltage drop is a huge red flag for a nearby short circuit. Then there's differential comparison, which is super cool. It uses Kirchhoff's law to compare the current entering a specific zone to the current leaving it. If they don't match, boom, it knows a fault is bleeding energy inside that zone. Finally, it uses impedance measurement. It divides voltage by current, and if a fault happens, that apparent impedance drops sharply. It is doing all of this insane math in literally a fraction of a second.
But here is the absolutely crucial limitation of our detective. The brain might be smart enough to detect the problem in a millisecond using all that advanced math, but it has zero muscle,
None. It simply lacks the physical capacity to actually step in and interrupt that massive fault current flowing through the main lines.
Section 3. The muscle. Circuit breakers.
And this is exactly where our story shifts to pure action. We need heavy machinery. We need the muscle to step in and physically stop the rogue energy from melting the grid. Enter the circuit breaker, which executes a rapid, split-second, three-step takedown. Step 1, the trip command. The relay fires off a signal that energizes a trip coil inside the breaker. Step 2, contact separation. That energized coil pops a heavy-duty mechanical latch, causing the breaker's contacts to aggressively, violently pull apart. And finally, Step 3, arc extinction, which fully isolates the network.
Now you might be thinking, okay, you open the contacts, the circuit is broken, story over, right? No way. Electricity fights back. Because this is happening under extreme fault conditions, the voltage stress actually ionizes the air between those separating contacts. This creates a terrifying, highly conductive, superheated electric arc of plasma. So get this, the massive fault current just continues to flow right through the open air even though the metal contacts aren't even touching anymore.
To actually win this battle, the breaker has to literally blow out an electric fire using some of the most extreme engineering on the planet. Breakers use specialized mediums to suffocate that arc. Some blast SF6 gas, sulfur hexafluoride, at high pressure right across the arc to absorb the free electrons and kill it. Others are vacuum breakers, which open the contacts in a pure vacuum. Since there are literally zero gas molecules in a vacuum to sustain the ionization, the arc dies instantly. Older designs use high-pressure air or insulating oil to literally sweep those ionized particles right out of the way.
Once that arc is finally extinguished, it's over. Just like that, the crisis is averted. The violent anomaly is completely isolated, boxed out. And because of this incredibly high-speed teamwork between the brilliant relay brain and the muscular circuit breaker, the rest of the healthy grid just continues feeding power to your house completely uninterrupted. In fact, you probably didn't even notice your lights flicker.
So next time you flip a light switch, I want you to consider these invisible wars being fought for you every single day, literally at the speed of light. And it really leaves us with an exciting question to ponder. As our grid gets increasingly complex, how do advanced, futuristic devices like StatComs change this high-speed battle? How is tomorrow's advanced tech going to further evolve this protection scheme to handle things like renewable energy and way heavier loads? It is an absolutely fascinating frontier. Thanks so much for exploring the anatomy of a grid crisis with me today. Keep learning and stay curious.